Thank you. Thanks, everybody. So what am I going to talk about today? So what we're going to start off with, I think I haven't seen the following presentations, but I can kind of, I think from what I've seen, they're going to talk about performance, early performance exploration, analysis, maybe architectural TLM kind of level. What I'm going to talk about is more specifically at the RTL level. So this is not going to replace what you might do at the architectural level, but it gets down to the very, obviously, cycle accurate measurement of performance. I'm going to talk about how we can go about this in a systematic way. Specifically, I've got an example that's based on an ARM CPU subsystem, and I can show you some of the results. I was hoping to do a demo, but it's not really worked out. But we actually have results we can show based on UVM test benches. So here we've got a not untypical CPU subsystem diagram. Obviously there's some simplifications in these diagrams that aren't shown, quite substantial ones. Mm-hmm. The key thing being that we have, in this example, so this is a mobile application, ARM's CCI, so cache coherent interconnect, is designed for mobile, so lower power applications. And you're defining in this its architecture coherent and non-coherent domains, and you decide when you stitch this CPU subsystem together which IP is going to be communicating with memory in a coherent or non-coherent way. And that's key because obviously the coherent domains share caches in the processor clusters. So the L2 caches are shared both between the clusters, but also potentially the GPU, or you can decide if you've got high-speed comms, you can make that coherent. I picked a mobile application because in some respects the challenges are more complex. Your IPs tend to be quite heterogeneous in terms of performance requirements. You have maybe displays and PCI Express, maybe a range of things. In the enterprise domain, they tend to be generally more regular. You have with multiple high-speed reading. On this in simulation, it doesn't take that long. You can drive traffic and start to configure the other IPs in your system to see what impact those configuration choices have. Now you can see here we've got active VIP driving the traffic. We've got some passive VIP on the downstream interfaces and a passive scoreboard. I know it's an eye test is the writing on this, but a passive scoreboard that can actually track transactions through the system. Because what you want to know is not just the latency from the master's perspective. You want to know, for instance, and CCI is a case in point, did a transaction have a cache hit, as in a snoop hit into the L2 or a snoop miss? What was the different latency based on snoop hits, misses? And ultimately, what else was going on in this environment to try and debug it? If you've got a debug, it's not just finding performance problems, it's then how do you actually approach the debug problem? What other information do I need from my IP? You know, for example, was the DDR controller doing a refresh when a particular transaction took a long time? That could be a very valid reason why a transaction takes longer than you expect. So we've been working very closely with ARM on a systematic approach to how you gather all the data, even a system that essentially looks quite simple. There's an awful lot of data you can gather on this. How do you gather the data? How do you manage it? How do you analyze it, debug it, and use it to tune your system? Okay. And the first thing that we suggest you do is to characterize the performance. And this is very simple. It's take path by path, so only one path active to memory at any one time, path by path, and actually analyze the bandwidth, latency, maybe sweep outstanding transactions. if you're familiar with the AXI protocols from ARM, they allow multiple transactions to be in flight at any time from one initiating master. Now, obviously, the more you have in flight, there is actually hardware you have to configure to store all of that stuff. So when you configure the interconnects with Amber Designer, you actually say, I want to support 32 outstanding reads and 16 outstanding writes, whatever. You configure it, but it's real hardware you're changing the size of when you do that configuration. How do you know whether you've over-engineered or under-engineered that? And so one way of doing it is to actually use the VIP to generate streams of traffic where it does 1 outstanding transaction, 2, 4, 8, 16, and you can actually see the point at which the performance saturates and decide, right, if I can never get better performance with 16 outstanding transactions, there's no point configuring my hardware to support more. It's just wasted hardware. But conversely, that might be more than I need. I can actually reduce that. So again, doing an outstanding transaction sweep can be beneficial. What you want to do is all of these tests with multiple burst lengths in the transactions, reads only, write only, read write. So the amount of data you gather is actually quite daunting, but the idea is we've built a GUI that allows you to very easily analyze that data, because it's overwhelming. And this is just a basic, characterization is a basic test. What does it actually tell me? Well, it tells me, firstly, that I've connected up all my IP correctly. That's actually not as dumb as it sounds, because you can connect it up and functionally it'll work, right? But has it worked in a performance sense? Have I set the clocks right, the right clock domains? All these really simple things can fall through quite easily functional verification, because it doesn't, the clock speed doesn't get checked in a typical UVM verification environment. Okay, so there's lots of other aspects. The other thing is that most customers will put their own bits of glue and magic between all of these pieces of IP. So it may look like a box of Lego that I just got from a supplier, bolted it together, it should all work. Well, actually, there's lots of little bits and bobs people add in for the good reason. The basic characterization test will check all of that for you. Okay, so you know if the bandwidth from a particular master to the memory isn't adequate in this test, it's never going to be adequate. This is the best it can ever be. Okay. So what do we actually get out of that? Well, as I said, we get a ton of data. So we have a way of analyzing all of this data and giving you, in this particular example, we're looking at the first column is max bandwidth graphs for read-only, write-only, and read-write. So the interesting thing is you can see they look quite different, which is immediately, visually, you kind of go, hold on, okay. And you see the middle row is latency over time. So for write transactions, they're straight lines. It's utterly predictable. Well, writes are posted, okay, so it always happens instantly, okay. For the reads, it's a round-trip delay, and there's variability in this. And so that asks the question, well, you know, what's the address patterns you're using and how do they affect the performance of the DDR controller? It's a very complex environment to actually understand the min, max and variability of latency. The other thing that jumps out on these diagrams when we went through them was that the read bandwidth is actually quite a bit higher than the write bandwidth, and that's to do with a complex issuing limitation of some of the ARM IP. So you can only get about 5 gigasecond of write data, but I mean, but it is capped lower than the read data. What we also discovered is that, in some senses, the interconnect can be the throttle, not the DDR controller, depending on which particular clock frequencies you check, you set up, which DDR standard you use. You can change whether it's the interconnect that's throttling the performance or the DDR throttling the performance. You would hope that it would be the DDR because you want to run that as fast as you possibly can. However, Not every system is the same. The same for minimum latency, and this gets interesting. Again, we looked at this and sort of went, hold on a second. For writes, we've got consistent latency, and reads, we've got these blips. When you actually go and research into it and figure out what's going on in the simulations, it was very quick for us to realize it's a DDR refresh. So as the DDR refresh pings in, suddenly the transactions take a quite dramatic hit on latency. And that's something, you know, I think a lot of the tool learning is about learning your IP. Your IP is a complex, it's almost getting to like analog, right? It's not, this is exactly the performance I'll get at all times. It won't be, right? It's a real complex environment. And the tool, through the visualization, helps you dramatically learn more quickly what the characteristics of an IP is, especially if it's a third-party IP, right? Do you get in a data sheet this kind of stuff? You don't. It will say peak bandwidth is 8 gig a second, but what's the actual real behavior when you put it in a system? And I think that's something it's very hard to get out of a high-level model. Now, you might argue this is a lot of work, also maybe close to when you're trying to get to tape out. So one of the challenges is how easy is it to build the test benches to do this, and how early in the project can I do it? Because knowing some of these things might be valuable earlier in the project than close to tape out, when you might not be able to change something fundamental. So what we've built is a tool that automates the assembly of the test benches and a lot of the other pieces that you need to do this analysis. And we're able to do this because if you look at the DUT we're talking about as a black box with amber interfaces on it, it's actually, you just need to know what the amber configurations are to be able to automate some of this. So for example, ARM's Amber Designer product will spit out IP exacts that describes the interconnect, both from a protocol point of view, an address map point of view, pretty much all the things you need to be able to automate a test bench. So from Amber Designer, we can take IP exact, generate a performance test bench or a verification test bench if you want to just use it for verifying your subsystem. We also automate the creation of the characterization tests. So all of the tests you've seen, that I showed the data for there, the min latency, max bandwidth, outstanding transactions, we generate a huge wodge of tests automatically for you because we can, so it just saves you the task of doing that. You then run that test bench in simulation and it dumps the data out into the GUI. That's basically the flow. So now you can actually take, let's say you want to start with CCI. If you don't know how it works, you can go and just use that starting point, but assemble out the subsystem either using IP exact, or for some customers IP exact is still not got the adoption, I think, broadly. I don't know, it'd be interesting to get how many people here of IP exact assembly. Anybody use IP exact assembly? No. Okay, so it's still in its early days. Interestingly, ARM's just bought Duolog, so that. Yeah, I imagine there's a few online. But ARM just bought Duolog, who are an IP exact assembly, IP assembly tools they provide. So by automating the assembly of the CPU subsystem, you can automate the creation of test benches that go along with that. However, a lot of customers we have don't have IP exact, and so we have effectively a spreadsheet. You can, from a spreadsheet, define the black box that is your subsystem, and we'll generate a UVM test bench automatically and tests automatically for it. Okay. Am I ahead of schedule? Am I? Oh, crikey. I didn't realize I had that long. Okay. Here we go quickly. That's okay. So we talked about, so in the previous test bench we were running these characterization tests. That's kind of the first step. Okay, so we can fully automate that, but it is very basic. It's just going to tell you, have you broken something in the assembly of your IP? Have you configured it correctly? It doesn't tell you everything about whether you've configured it correctly. If you remember this diagram where we've got multiple masters active, the key thing here is that we need to define QoS. We need to define the quality of service of our system and how it behaves. It's a dynamic, you can think of it as a dynamic arbitration. And it affects the interconnect components and the DDR. All of them have contributions to be made in this. And analyzing this is the next step. Right, so what do? Well, we create a test bench that allows you to model workloads. So what do we mean by workloads? So we want more than one master to be active, and we want to try and model the traffic in a simplistic way, and there's a good reason why we want to do this simplistically. Realistic traffic, trying to analyze what's going on in a realistic traffic scenario is a nightmare. So what you want to do is firstly distill the essence of an IP's behavior and say, okay, let's say a display, it needs 2 gigasecond of read data with this kind of address pattern. That's probably enough information for you to start trying to configure your system to cope with that. Not only cope with it, but debug if something goes wrong, how do you debug it, right? That's the whole essence of trying to start simple and add, if you like, realism into the process, because the realism makes it very difficult. So what we do is for each master, you would say, I want this much read bandwidth, this much write bandwidth, this is the address patterns, maybe even down to the degree of these are the Amber transactions I want it to use, because you know your IP has that kind of behavior. And with them all active, you now want to enable quality of service and see what bandwidth is actually achieved. So what you will see is, this is what I requested, this is actually what I got. And that's where life gets more complicated, because your use cases here, your traffic workloads, typically are going to be ones that are pushing the limits of your system. And what you really want to know is, how does my system degrade when it gets to the border of working or not working? Does it get to the edge of working and catastrophically shut down, or does it gracefully degrade? In other words, is it giving the masters the right bandwidth allocation based on their needs? And obviously the QoS system that you employ is about allocating priorities to the masters that can be dynamic. So you can say maybe the display, and obviously one of the masters up on the far right would be modeling the display. You could say I want a QoS level of this, but it's got scope to bump up the priority if it's not received a certain amount of data by a certain amount of time. So all of these IP, the interconnects and the DDR tend to have regulators in them that are dynamic, and they try and satisfy the requirements that you've given it to the best of their ability, up to the point when they start to degrade. I can't show you the screenshots of this because I don't have them, I've not put them in the presentation, but we have the same kind of ability to analyze the results and compare. So you could say, here's QoS settings, here's other QoS settings, and actually compare whether the bandwidths are better or worse. Okay, so in summary, it's a complicated area, and building the test benches and the models of these traffic generators is a lot of work, and ideally you want to be able to do it early. We're proposing a 3-step process where we do characterization, you do workload modeling, which is static. So you would say, here's a master, it's got this bandwidth requirement. Once you've done that, and if you're satisfied with that, you could even go to the sophistication of building in UVM sequences that will actually make it a dynamic use case. So IPs can fire up and use some performance of the system and then go to sleep. And that's what we would call kind of full use case. You may even want to do that with software, as in run on a Palladium or run on a fast platform and actually run real software rather than try and model the CPU, because the CPU is probably the most difficult thing to model. It's very, very use case dependent. Working very closely with ARM, so a lot of the core link interconnect products we support out of the box. So you literally, if you want to configure a NIC 400 or a CCI, you push a button and you get a test bench out with no actual code you have to write yourself. We do support the ability to create test benches with non-ARM interconnect if that's what's required. Any questions?
Your performance was better than the expected.
High performance.
Any questions from Bristol?
Do you support CHI as well as?
You need to repeat it as well.
So there's a question about whether we support CHI. So currently we have VIP for CHI and we have the scoreboard. We don't support automation yet. It's really about us. The way our automation is built, we basically have to package that VIP and then it becomes available. But we do plan next year to work on CCN, which is a CHI-based interconnect.
A question as well. You talked about the refresh on the DDR, but I would have thought if you're trying to do performance, wouldn't you just switch that off and do it as if there wasn't any refresh to try and get your absolute numbers, and then know the impact?
Well, so that's a very if you want to get the question is about DDR and refresh and whether you wouldn't just turn that off. Yes, you could do that, and the tool will tell you the min-max latency, so you'll see in the periods when there's no refresh the min latency. There's also, DDR's complex because you want to probably also do what's the performance with in-bank hits, in-row hits, in-column hits, out-of-bank hits, right? The DDR is so sensitive to address patterns that is crucial as well, and we're building some DDR efficiency tests is the next thing we're adding to this, simply because that's another whole raft of tests that you need to give some sense of what's the best you can achieve. You don't know when your software is executing whether you're going to happen to hit a refresh or not hit a refresh, so you want some realism in there. So it's a complex, DDR is a very complex question.
Is this automated?
The DDR efficiency tests, yeah, that's the idea, is we'll automate them. I mean, obviously we have a DDR controller, so we're testing it on ours as well as ARMs. But yeah, and the configuration of so if you look at the way DDR is configured, you tend to have, here's my address, and I map the row, column, banks, and each DDR has lots of different configurations. Once you've specified that, we can automate the generation of the tests for you to do continuous row hits or row misses, bank hits, bank misses, all of that. It's very easy, it's just address generation.
The other question is, there seem to be a lot of parameters involved in this, and half the challenge is to manage all the different parameters and make sure you're trying to minimize the number of parameters you use in combination, otherwise you're going to get a classic explosion. You just have to repeat that.
Yeah, so there's a question about the number of, are you meaning configuration parameters, yes, or general? Yes, but that's an explosion in IP in general. There is an enormous number of configuration parameters, especially commercial IP, because you're trying to produce an IP that satisfies everybody's possible configuration. So I would say, I know for sure in our IP we have options for configuring command FIFOs, write FIFOs, read FIFOs, hundreds and hundreds of them. The difficult thing is I don't think it's always clear which are the important ones and which are the non-important ones, and that's something we want to help the users understand. When you get an IP, can you do some characterization of your own and understand which are the important ones, knobs to twiddle, and which aren't the important ones?
And one last question for me, what's the sort of simulation performance of this?
So there's a question on simulation performance. From a subsystem point of view, it's pretty, you're talking about hours or less than hours. We have some customers who run this on the full SoC, full application, mobile application processor. Obviously taking control of the masters, so for instance the processors aren't active, but that's still doable in simulation, 7 or 8 hours. It's not, you don't want to run lots of them. We're working on how to apply a mechanism to apply this to Palladium so that you could run real software loads and measure. So for instance you could run an Antutu benchmark and actually take a sample of what numbers you're getting from that, rather than, because that's actually what people want, but that's even later in the day when you're running software on it. I think the value of that in general is learning for customers who build derivative and evolutions of platforms. You can go and look at your previous generation and actually measure things to learn about how to do it better the next time. I think that will be the most valuable part of that. Okay, thank you.
Okay, thank you very much. Thank you.